Hi, everybody. So today we're going to talk about linear regression and correlation. We're going to go over the theory, and then we're going to take a look at the example that we can use with Excel. So again, let's take a look at linear regression and correlation. As professionals, we want to see the impact of two or more variables and how they're related. We can look at grades on a second math test and what it would relate to for a final. Is there a relationship between these two? And how strong is it? So one, is there a relationship? And two, how strong is it? We also might want to take a look at our income and see if it's determined by our education or our profession, years of service or experience, or our ability. So again, we might look at income and education. The more income or the more education you have, does that mean you're going to have more income? So we could say x-axis is education and y-axis is income. So if you have high school, college, university, postgrad, the more education, does that mean you're going to get more income? We don't know. So the type of data that describes this example is bivariate. Bi meaning two variables. So you could have other variables, multiple variables, but we're going to just focus on two in this linear regression. We're going to keep it simple. Now, the x variable is our independent, the x, and that's on the x-axis. The dependent variable is y. So independent is x, dependent is y. We're going to see how strong that relationship is. Now, you've probably seen this before. This is a typical linear equation. It describes a line. Y equals A plus BX. Now, again, Y is our dependent and X is our independent variables. This is also referred to as the slope, and this is the y-intercept. And you've probably seen this linear equation before, probably in high school. So the linear equation forms y equals A plus bx. It's a straight line. Any line that's not vertical can be described by this equation. So any line can be described that's not vertical. So that's not straight up and down. So some examples of linear equations. So for instance, this is a word problem. Aaron's word processing service does word processing. The rate for the services is $32 per hour, plus a one-time charge. The total cost to the customer depends on the number of hours it takes to complete the job. Find the equation that expresses it. So when we take a look at this, again, always good to graph it out, x, y. The bottom axis is the number of hours, and the y-axis is the cost. Now the intercept is the one-time charge. That's your fixed charge. The intercept is the one-time charge. So that's your fixed charge. That's where if you have 0 hours, you're going to still have to pay that. So that, let's say it's right here, 31.5. And then, as you have more hours, your total cost is going to go up. So straight line here. So if we talk about how do we express this in an equation, is y equals, now the equation, and again, sometimes there's different variables used for this. We'll keep it consistent. A is the intercept, so that's your fixed cost, 31.50, plus B is how the slope goes up, that's slope, a part of the equation. So for every X, for every hour, it goes up by $32. And that's our equation. Again, the A is the y-intercept, the B is our slope. You can see some various graphs. A is a positive, it goes up, X, Y. B is horizontal, that means it's steady. So again, A, the slope is greater than 0. Where it's horizontal, the slope is 0. And when it goes down, that means the slope is less than 0, so it's negative. Negative. So this could be an example of a negative one, is hours gaming. And this Y could be your marks. The more you game, the less time you study, so your marks go down. This one could be marks. This could be studying. The more you study, the higher your marks go. Now, scatter plots is just a set of data points. So typically, when we look at linear regression, it's between the two variables, y and x. So a scatter plot is just plotting these points. So we plot these points. So we may have y and x, and we have various data elements, and we're just plotting them along the respective x and y axis. It's good because a scatter plot can show us the direction of the relationship between the variables. So again, it can, when we plot these points, it can tell us what's the relationship, because typically you get plots, or you're busy graphing these plots, then you can come up with your line. So again, we want to see if there's a relationship, a linear relationship, if it's positive, negative, or if it's horizontal. So, no relationship. Positive, negative, no relationship if it's horizontal. So we can take a look at these trends. Okay, we want to see these patterns in these scatter plots. So again, your x, y, as x increases, y increases. That's a positive relationship. This one, y, x. It's a positive relationship, but we got one deviation. Got one outlier. This is a x, y. We have a negative relationship, it goes down. And it's strong because these data points are close together with the line. This is a negative, weak. It kind of goes down. If you plot a line of best fit, it kind of goes down negative, but it's weak. You have lots of deviation. So it's weak. There's not much deviation here. This is exponential growth. We can't use linear regression for that. That's exponential growth. And this is no pattern. You really can't. It's not like that. It's not like that. There's no pattern. Really can't use linear regression for that. So linear regression, you can find out what the pattern is. Get that pattern. So when we draw a line on the scatter plot like I did, that could be calculated through a process called linear regression. You really don't get your ruler out and try to do this. We can use some tools for that. Now, the line of best fit is that line in our linear regression. It's the line of best fit. It's the line of best fit or the least squares line. You might have learned that term, least squares. It fits, that line best fits between those scatter plots. So again, here we have y, x, the third exam score, and an indication on the final. So the more you get in the third exam, probably you'll get a higher in the final. X is independent, and y is what's depending. Y is always the dependent variable. You can eyeball this, but again, we're going to get least squares regression line. Now, y hat is the estimated value of y. It's the estimate, the line. So it's the estimated line. We might have a point here, y, 0, but y hat is our estimate. And again, we have our y points, and we have our x's. Linear regression is the process of getting the best fit, the line of best fit, coming up with that linear regression equation, the best fit line. And we really want to have that line that reduces, the best fit that reduces it. We don't have it up here because we have a lot of variation. We want to have this best fit. Now the line of best fit, it minimizes the squared errors. So it minimizes the errors. The errors are made as small as possible. So these are your errors here. The distance between your points and the line. So you want to have that line that minimizes that. Now, typically you're going to get a data set with x variables and y variables. And you're going to be plotting it. Typically, you'll have a chart. Here's your x's and your y's. So 10, 20, 30, 40, 50, 60. In this case, you might start at 60, go to, I don't know, 80. And this might start at this point, 0 to we could start 180, 190, let's say. So we plot these points. And again, it would be, looks to me, you'd plot these points. It looks to me they would go up. But we don't have to do this manually. This is our data set. Now, So we're going to graph that, and I'll show you what tool we use, so don't get worried about where we're going to be calculating this. Don't worry about mapping it out. What we can do is we're going to use a linear regression tool, and I'll show you that. Now the correlation efficient, there's another number we need to kind of be aware of. When looking at the scatter plot and seeing the lines, how can you tell if the line is a good predictor? That's the correlation coefficient. It's another indicator besides the scatter plot to understand the strength of the relationship. So it's the correlation coefficient. It's R. And we'll take a look at calculating. We don't need to do this by hand. We suggest never to do it like that. There's a tool we can use. But the important thing about the correlation coefficient the value is always between -1 and 1. So it's always between -1 and 1. Now, the closer to the -1, that's strong negative relationship. If it's closer to +1, that's a strong positive. If R is 0, that means there's no relationship between the variables. So if the R equals 1, it's a perfectly positive correlation. If it's -1, it's perfectly negative correlation. These really don't happen in the real world. So again, closer to 1, the stronger it is. What the signs mean, a positive value means that it's a positive relationship. When X increases, Y increases. That's when R is positive. When it's negative, that's your negative relationship. It goes down. It doesn't suggest a cause. It just gives the correlation. Now, interestingly enough, your R is going to be the same sign as your slope. So if your slope is negative, it's going to go down. Slope positive, it will go up. And your R will be negative, R will be positive. So if you take a look at these examples, positive correlation, positive correlation. So R is greater than 0 but less than 1. Negative correlation, R is greater than -1 but less than 0. So R is negative, R is positive. In a horizontal line, there's 0 correlation. So you would have a R equals 0, or slope equals 0. So this is the positive slope, negative slope. And you can see the negative slope here, the positive slope. Now, the other thing we can do the R squared. Now, it's a really interesting thing when we take a look at the coefficient of determination. That's R squared. Simply squaring the R. It's the square of the correlation coefficient. Then we get the coefficient of determination. That measures the percent of variation. So the percent of variation in the dependent variable y, that can be explained by the variation of the independent. So again, it just tells us if we have a large number for R squared, that means a lot of the predictability of y can be explained. A lot of the y can be explained by the x variable. So again, when we consider an example where we have the line, this is our line of best fit. Now the correlation coefficient is positive. That's great, we have a positive slope, so we know that's right. The coefficient of determination is the square root, it's the square of the correlation coefficient, so we get that number here. And we interpret the correlation to determination as follows. So we can convert this to a percent. I'm going to round it up. So we can say, because of the correlation to determination, approximately 44% of the variation, in this case of the final grades, our y-dependent variable, can be explained by the variation in the grades on the third exam, which is x, independent variable, using the line of best fit. You can also twist this, and we can take it as 1 minus r squared. So we have 1 minus 0.44, 56%. We can say that 56% of the variation cannot be explained by the variation of the grades of the third exam. The final exam grades cannot be explained by the variation in the grades of the third exam. So 56, we cannot be explained by the variation. Now, once we have this linear regression line, and this is the line, again, y equals negative. This is the one that we have here. It's our linear regression line. We can use this to make predictions. So again, we can pop in any x to help us find out what y is. Again, x was the third test, and y is the final. So if we knew what a student got from a random student got on the third test, we plug it in, and in this case it's 73. Okay, we plug it in. It looks like this is marks, scores. So we plug in 73. If we do the math, we get 179.08. So we can predict that their final mark would be 179.08. And we can use this prediction. Again, you can use this prediction, plug in what any third exam score to get the final. So again, if we wanted to do A, we would say just plug it in, do the math, and whatever this turns out, it would give us our predictability to what their final score would be based on 66 in their third exam. Get out your calculator. You can take a look. So negative 173.51 plus, doing the math, 318.78. So we'd get 145.27. So we could say that would be their final grade. And again, we can use this to predict. That's what we got. Now, something to note. So there's a student who scored a 90. Now, if you take a look at our scores, you're going to see 90 is outside of our range that we have here. So 90 is outside. So this example here, they kind of trick you. So they're asking what if a student scored 90 in the third exam? It's outside of the data range of the observed values. So we can't reliably predict the final exam score because we had points here. This is the final. This is the third exam. And we kind of had points, kind of had data points up to here. We're 60, 65 to 70, let's say. But we're asking for 90, so it's up here. Now we could have this chart. We could assume that it's like that. We can't reliably, because it can be unreliable when you predict something that's outside this range of data that we do have. Just keep that in mind. If you ever you can continue on, but if you find out that we're trying to predict something that's outside of the range of data that we have, it becomes unreliable. Make a note of that. Thank you very much for watching, and we'll see you next time. Hi everybody. I'm going to show you how to use Excel to solve your linear equation problems. So again, how you can use Excel to solve linear equation problems. So typically open up Excel. So you can open up Excel. And I'm going to be pasting the data set here. So I copied the data set from my problem and I just pasted it in Excel. So you can go copy, paste your data set if it's listed in nice columns, your X and your Y columns, nice and straightforward. Now, typically you're going to have it listed like this. And now we can do a regression. So typically you might have to kind of put it into this format. I'm going to pretty this up, kind of make it look nice. There we go. And I pasted this from the Blackboard, and I'll use this as an example. So we have our X and Y data points. Now, we want to find the line of best fit. Now, we're going to do this by going to Data. So go to Data and go to the Analysis Tools. Now, when you do that, I'm going to look at Analysis Data Pack. I'm just going to take a look here. Analysis Data Packet should be correct. Okay, so I have the data tools. Just double checking that. You don't need to do that, but I always like to check. Now we have data analysis. So I'm going to click data analysis. Now when data analysis is clicked, I'm going to choose regression. That's linear regression. I'm going to choose regression. I'm going to go OK. Now what it has is it says input the Y range. So I'm going to click here, and here's the Y range. The numbers, press enter. Now I'm going to do the X range. Select it, press enter, and have what I need. I think I have all of the information that I need. And I'm going to put the output, I'm going to put the output right here and go OK. So this is the output from the regression analysis. Puts it all nicely. Here's the intercept and the X variable, our slope. So we can say it's Y equals A plus BX. In this case, Y. So that's our formula. So A equals 3.1 A equals intercept negative 3.6, and the B, the slope, is 3.1. Okay, so we could say, what is Y? I'm going to type this out, y equals, 3.6, got that wrong, typed it wrong, 3.6. Y equals negative 3.6 plus 3.1 times x. So you can do, so what is y? What is y if, depending on what x we have? Now in this question, we're looking at tree trunks. Okay, so these are tree trunks. And suppose you collected the following information that we collected here, for the diameter of the tree trunk and the height. What is your estimate of the average of all trees having a trunk diameter of 7 inches? So what is y? What is y when x is 7? So this is, x is our dependent. So that is diameter. And it's just height. Okay, so what is the height? I'm going to type this out. Equals, and I'm going to just reference these variables, equals that plus b, and I'm going to put Bedma rules. So that times, and I'm going to make a spot for x. Let's say x is right here. I'm going to just fix that. So x, what if x is, and they say 7 inches. There we go. So let's do that again. So this is our formula, line of best fit. We have it here. And A is from the intercept. I'm going to color code A. That's our A. B is the slope. So I just copy them over here. X is what we're looking for, or X is what they give us. So they're saying, what if the tree trunk is 7 inches? What is Y? What is Y? We don't know. So now we use our formula again. I'm going to type it out. Equals 3.16 plus B times X. Make sure you do the Bedma rules. And there we go, 18.1. So what that means is the estimated height of all trees having a diameter of 7 inches is 18.1. And we give it a unit of measure. They don't give a unit of measure, so let's just say that's tree height. So that's the height. We'll just say 18.1. They don't give us a unit of measure, so the answer is 18.1. Thank you so much for watching, and that's how you use the linear regression tool in Excel. Thank you again for watching.